Welcome once again to Geometry. Tonight we're going to talk about arc length and sector area. So let's go ahead and get started. We're going to start off with arc length. We talked about arcs previously. Tonight we're going to talk a little bit more about them by not just finding their measures, not just how many degrees they are, but actually going so far as to find out how long they are. So the definition formally is the distance along an arc if you measured it in linear units. So if you measure it in inches or meters, like if you literally took a string and you went right along this red arc between A and B, and how many inches long would that be? That's the length of the arc, as opposed to the number of degrees it is, which looks like this one's probably about 80 degrees, but it's going to be the length, not the degrees, what we're looking at. The formula is pretty simple. I put it here, but really all it is that you want to find out how much of the circle your arc is. So you take out how many degrees it is. So like if this is an 80 degree arc, we put 80 there. Out of the 360 degrees total, so that gives you a fraction, what percentage of the circle you're dealing with. And you just multiply that by the circumference of the circle, or pi d. So you take the entire circle and you just do only a fraction of it. So you have to find out how much of the circle you have and take that fraction of your circumference. So let's do a quick example. I have an arc here, GH, and we're trying to find the length of that arc. We know it's 40 degrees, and we know that our circle has a radius of 6 meters. So I'm going to take my little formula here, the arc measure over 360, so find out how much of the circle it is. It happens to be 40 degrees of 360. And since my radius is 6, my diameter is going to be 12. So 40 over 360 times 12 pi. I simplify the 40 over 360 to get me 1/9. So 1/9 times 12 pi gives me 12 pi divided by 9. It's the same thing. And then I just kind of reduce that to 4 over 3. So 4 pi over 3. Multiply that out. I get about 4.19 meters. So that means my arc is about 4.19 meters long. It's 40 degrees, but it's 4.19 meters. Okay, so that's arc length. Next we're going to do sector area, which is basically the same process. It's just that instead of dealing with the arc, the distance from A to B, we're dealing with the area that arc kind of represents, how much of the circle the area would be. So to do that, we take the two radii that would go out to the arc. So the formal definition is the region bound by two radii, so CA and CB, and their arc, the arc that they intercept or they cut off of the circle. So take that part here, and we find the area of that orange shaded region there. And the formula is basically exactly the same as what we did for arc length. We're still going to take what percentage of the circle, so arc measure over 360 degrees. But instead of multiplying by the circumference, I'm going to multiply by pi r squared, which is the area, because I don't want to know how long it is from A to B, but I want to know how much of the circle's area we're dealing with in this shaded region here. So I take how much of the circle, the arc measure over 360, so it gives me a fraction of the circle, and multiply that by the entirety of the area. So that fraction of, and of in math typically means multiply, the area of the whole circle. Let's do an example. Here we go. We have this little green sliver of the circle I'm looking for. I know that it's 36 degrees of the circle is the arc there, and I have a 16-inch radius. So take my little formula here. I got arc measure over 360 times pi r squared. I plug in that arc measure 36 degrees, and then I know my radius is 16. So I can reduce my fraction. 36 over 360 is 1 over 10. And 16 squared is 256. I then multiply that out, so 256 pi over 10, because multiplying by 1/10 is the same thing as dividing by 10. Then I kind of reduce that fraction. I can divide by 2 on the top and the bottom, so I get 128 pi over 5 if I wanted it in fractional form, or if I didn't want to round it, that's about 80.42, so a little less than 80.5 inches. Is the area that we're dealing with there. And of course that would be inches squared. So then we're going to move on to segments. And I know you're thinking, wait a second. Mr. Olivier, we've talked about segments. I know what a segment is. You've harped on the fact that segments and lines are different, but now you're talking about a totally different kind of segment that's not even talking about a shape per se like we've known, but this totally weird little sliver of a circle piece. I know, it's one of those examples of we're using a term in a way that you didn't use it before. And I warned you guys at the beginning of this unit that was going to happen, that we're going to end up using a couple of terms in ways that you didn't think of before. We already experienced that with tangent. It doesn't necessarily mean opposite over adjacent only. It also means intersecting the circle at exactly one point. Here, a segment of a circle is, as you can see, this little green shaded area. So what happens if you take a chord and its corresponding arc, and you look at just the area they form. So you take the arc RQ and chord RQ and use them to form a little kind of chunk out of the side of a circle there. To find the area, that's kind of tricky. It's going to be a multi-step process. Essentially what we're going to do is find the entire sector that arc would form, so the entire sector QPR, that whole area there, and subtract out this triangle QPR. So we take the whole area and subtract the unshaded region. So you guys have kind of done this before with shapes, but we're just going to kind of take it a step further. So the first step is to find the area of that whole sector. So here's my shape. I have this nice little right angle, which gives me 90 degrees. It's a nice even measurement for my arc. And then 4 meters long is the radius. So I'm going to plug that into my sector formula. Areas arc measure of 360 times pi r squared, just like it was before. I know I'm dealing with 90 degrees, which is a quarter of the circle, 1/4. And radius is 4, so 4 squared is 16. So I end up with 16 pi over 4, which reduces to 4 pi, which is about 12.57 meters. And I'm going to leave it in the rounded form because when I take the next step, which is find the area of that triangle, I'm going to need to have it rounded so that I can subtract them. So step 2, take that same little triangle there, triangle RTS, that right triangle there. Area of a triangle is base times height divided by 2. So since the right triangle and RS and ST are the two legs, the kind of base and height, if you look at it sideways, they're both 4. So my base and height are both 4. 4 times 4 divided by 2. 16 divided by 2 is 8. So I have an area right there of that triangle of 8 meters. So I'm going to take that triangle and I'm going to subtract it from that whole sector to find the area of the segment. So my formula there again was area of the sector is segment is area of the sector minus area of triangle. So the area of my sector was 12.57. The area of my triangle was 8. Subtract those to get about 4.57 meters squared. Is that little green segment section there. So not too many topics, but each one of them has kind of a formulaic process. Just remember that the area of a sector and length of an arc is basically the same formula. The only difference is, are you talking about the circumference you're taking a fraction of, or are you talking about the area you're taking a fraction of? And then segments, that 3-step process. Find the sector, find the triangle, and subtract. So I guess I'll see you guys tomorrow, and have a good night.